I'm going to do a demo. It's a follow-up to the reflection-refraction demo that I did. We're going to prove the equations for converging and diverging lens image formation using pins as well. Pins and paper, very simple equipment, but you can do quite a lot. So I'm going to have a converging lens like this. The converging lens will be bulged rather in the center. I'm going to draw the converging lens on a piece of paper. Then I'm going to put a pin here, somewhat a distance away from it. And then from the other side, I'm going to view the image of that pin. Then I'm going to put 3 sets of 2 pins, wherever the image is. 3 sets of 2 pins that cover the image of that original pin. So it's going to look something like this. And then I'm going to go backwards and then find where the image of that of this pin is. It's going to end up that since I put this pin close to this converging lens, its image is going to be a virtual image. It's going to be on this side. It's going to be larger than the object, right? So if I go trace it backwards, I can find out where the image is, what its height is, and what its position is, and then compare to the theory. And then the same thing with a diverging lens. This one is converging lens. And then I'm going to do the same thing with a diverging lens. Put a pin here. This one, I'm going to do the same thing. Put 3 sets of 2 pins. Go backwards, find out where the image is, and the image is going to end up being in front of it, somewhere here. This one, the image is going to end up becoming in the back of it. So to get a little bit more detail, you can watch my videos on the theory section about converging and diverging lenses and the kinds of images that they give you to get a little bit more background information. Okay, so let's do the video. Now, this is my converging lens. So I'm going to draw the outline of the converging lens on the piece of paper. Then I'm going to draw a straight line through the center of the lens. Then I'll show you what I'm going to do next. Then I've got this lens, the outline of the lens drawn. I've got the straight axial line drawn. I put my object pin here. This is going to stand for my object, and I can draw a straight line like this. Imagine this is a candle with that height, like that. So then I'm going to come around the other side and see where the image of that pin is. Okay, so now I put 2 pins to cover the image of that original pin. So now I only see the front pin, and the image disappears. And then I'm going to do that at a different angle. So you can see the image there of the pin. And then these 2 are hiding. So you should only see the front pin now when I tilt it at that angle. So the image of the pin disappears. See, if I tilt it, you see, you can tell the image of the pin in the background. But now these 2 are hiding that. So okay, so now you can see the 2 pins that I put down, and then the 2 pins I put down, I drew the lines past the lens, and I want to see where they look like they're coming from. And so it looks like the image is going to be here. So what's going to happen, since this pin is inside the focal length of this lens will not be able to converge the light rays coming from this. So the light rays will come, bend, and they will look like, those light rays will look like they're coming from back there. So basically, this converging lens is acting like a magnifying lens, magnifying the image and creating a virtual image. So now the image is going to be somewhere here where they intersect. You see here, those lines. And then I can draw the image, go down, put an arrow like that. So it creates a upright virtual image, whereas this one is the object. Now to make sure, I can put another set of 2 pins, just to make sure that they meet at the same point. So I can tilt this again, and then do the same thing. So you can see here, these were the first 2 pins that I had. And then those were the other ones that you saw. And then this ones I put down. And then you see they cover the image that you're in the background. So you see, this is the image of the pin in the background. So when I put them at the right angle, they cover the image of those pins and you don't see the image. Now let's draw a line between those two pins. Okay, these are the last two pins that I put. And then I drew a straight line through them. And then they're going, then I followed it. The lines are going between the other two lines, the previous two lines. See, these are the last two pins. Just keeps going. And I want to see if they meet at the same place. You keep going and then they meet right there. So it gives us this virtual enlarged image. So that means the first two lines were good because the third one also meets at the same crossing point. So let's measure the distance from here all the way to the center of the lens, and then from the object to the center of the lens, and then do our calculations. So from the object to the center of the lens is 10, from 10 all the way to 20.2. So that's 10.2 centimeters. Okay, now from the image, you get all the way to here is 30 centimeters. Let's put a dot there. Plus another 21.5. 30, 21.5. It's going to be 51.5 centimeters. The next thing we need to do is measure the dimensions of the curvature of the lens. I put the 0 centimeter mark right here, and then all the way to here, 10.2 centimeters is 2.5. The thickness of the lens, 2.5. So what equation can we use here? We have 1 over distance of the object plus 1 over distance image is 1 over the focal length, right? I'm going to assume that the two sides have the same curvature and they have the same radius of curvature. So 1 over the focal length of a lens, if the lens is assumed to be a thin lens, which these are, they're not too thick, the 1 over the focal length of a thin lens is n minus 1 times 2 over the radius of curvature. 2 times the index of refraction of that lens minus 1, because the index of refraction of air is 1, okay? Divided by the radius of curvature of the lens. Now, since this radius of curvature primarily it's this way, it's facing to the right, that means the radius of curvature is going to be positive, right? So what's going to happen? Well, how do we calculate the radius of curvature from the dimensions that we have here? How do we calculate this radius of curvature? Well, the radius of curvature is the distance from the imaginary center of that circle to the lens, let's say the left side of the lens, right? And this also is the R and R. They're both R. So we can use an equation here. We can say, well, this distance here, right, is going to be what? If I call half the thickness of the lens A, right, that's going to be A. So this piece from here to here is going to be R minus A, right? Because from the center to the edge is the radius of the radius of curvature of the lens. So this piece is just going to be R minus A. This distance here we usually call B, right? That's the semi-major axis. And then the A is the semi-minor axis, right? So then you have your B and A. So we can say here that R squared is equal to R minus A squared plus B squared, right? That's the equation to find the radius of curvature of any lens, as long as you assume that the radius of curvature is the same. So I'm going to assume the radius of curvature of this other side coming this way is also going to be the same. So then you're going to have here R squared is equal to R minus, what's my A? A is half of the thickness, which is 2.5, so it's going to be R minus 1.25, R minus 1.25, and then square that, plus, and then you're going to have here B squared, so B is going to be half of this, which is going to be 5.1, right? 5.1 squared. Look what's going to happen. This R squared and this R squared is going to cancel, so it's going to be, we don't even need the quadratic formula or the quadratic equation at all. So we're just going to be 2.5R comes to this side, 2.5R, 1.25 squared plus 5.1 squared. Okay, and then that's basically how to calculate the radius of curvature of that. Of the lens, into an imaginary circle, you would find that from the center to the edge is equal to 11 centimeters approximately. Okay, so then apply this equation. 1 over f thin is 2 times the index of refraction minus 1 times index of refraction of glass minus 1 over the radius of curvature 11 centimeters. And that's going to be equal to the 1 over the focal length thin. So it's going to be... Okay, now notice, since my object is 10.2 centimeters, it's inside of my focal length. If it's inside of my focal length, the light rays will not converge here. A converging lens can only make a real image if the object is outside of the focal length, right? Then it's going to make a real image here. But since 10.2 is less than 10.57, it will not be able to converge it here. It will form a virtual image back there that is enlarged. And that's exactly what happened in our case. We happen to be a little bit shorter than our focal length, right? So now let's calculate what the theoretical what the theoretical distance of the image is. 1 over 10.2 plus 1 over di is equal to 1 over f. Well, 1 over f is just going to be, you could just put this number, 0.094545, and then subtract from that 1 over 10.2. Okay, so I get my theoretical distance of the image to be negative 286. That means this should have been even more enlarged, a lot more enlarged. It should have been somewhere over here, and it should have been a lot, very large. So I didn't get a very good result, but I did get an enlarged image here, 51.5 centimeters from the lens. In order to get a better result here, I would probably have to put my pin slightly closer because I'm too close to the focal length of the lens. And the little deviations from the focal length is going to make a big difference in where the image is. So in order to get a better result, you put the pin maybe at 8 centimeters, 7 centimeters, and then you can get a more exact result and a better result, okay? But the idea of the lab still worked out very good. The 3 rays of light met at the same point, and we got a image distance of negative 55. The reason it's negative 55, it's a virtual image to the left of the lens, right? So if I were going to do a percent error, I would put percent error equals 100% times, I would just take the absolute value of this, 286.22 minus 51.5. Take the absolute value of that, divided by 286.22. You could do it a little bit closer to the lens, and the human error would affect the result less, and you would get a much better result in terms of percent error. Now let's do the diverging lens. The steps are going to be very similar, except when we do the diverging lens, the focal length is going to be negative. And the image is going to be in front of the object. So I don't really need to put the pin too close. I could put the pin anywhere, and the image will always end up to be in front of the object, and it will always end up to be a virtual image, okay? Okay, I've already got 3 sets of 2 pins here. These 2 pins, these 2 pins, and these 2 pins block the image of that pin. This is my object pin right here. And the image is probably going to end up becoming somewhere here and smaller than the object. So then I'm going to take this out, take these out, draw straight lines. Okay, so now I've connected those lines. This is the first one, and then these 2 are the next one. I've connected that one. It goes through there. Then I've connected these 2 right here, like that, and then they connect at the same point. This is the image. So let's calculate, let's measure the distances here. Okay, the object was 17.7 centimeters from the center of the lens, 17.7, and then the image was 7.2 centimeters, 17.7 and 7.2. I went ahead and did all of the measurements. We already had the image, it was 7.2 from the center, and the object was 17.7. I measured the height of the object, 2.8, the height of the image, 1.3. Then I went ahead and measured the distance between the center of the lens, and then if I draw a straight line, that's my A value, right? And then my major axis is 4.2. So this is 1 centimeter, this is 4.2. So let's calculate the radius of curvature of this lens. So we have r squared is equal to r minus a squared plus b squared. So r squared is equal to, then we have here r minus a was 1 centimeter plus 4.2 squared. Because the front side of the lens, right, is facing this way, and that means the primary focal point of the lens is on the left side in the imaginary virtual world. There's two focal points. This one is the primary focal point, this is the secondary. The primary focal point is on the left side, and that makes the radius of curvature negative. So then we just put radius of curvature negative 9.32. So now let's go 1 over dO plus 1 over di is equal to 1 over f. So let's first calculate the focal length. 1 over f is equal to 2 times n minus 1 over r. 2 times 1.52 minus 1 over the radius of curvature, negative 9.32. Right? So then you're just going to get, so the primary focal point will be negative 8 centimeters to the left of the lens. The secondary focal point will be on the right side. Okay? But for the equation, we use the primary focal point. So then we're just going to have 1 over dO. My dO was 17.7 plus 1 over di is going to be 1 over f, and then 1 over f is negative 0.1115879. So now let's calculate what the theoretical di is going to be. Negative 5.95 centimeters. My di was 7.2 centimeters, negative 7.2. Right? So I'm not that close, but I'm within the, again, reasonable boundary for the sources of error for the eyeballing the pins. So you can see my percent error will be what? My percent error is going to be 100% times, then I'm going to do my results, negative 7.2, but I'm going to take the absolute value of that, minus the absolute value of this, 5.95 over 5.95. I could also do a percent error for the magnification, right? The magnification. So the magnification of the image, the theoretical magnification is going to be negative di over dO. So I'm going to put negative of the negative 5.95 over 17.7. So the theoretical magnification of the image is 5.95 divided by 17.7. So 0.34. That means the image should be 34% of the height of the object, right? 34% of the height. So that means it's the image is diminished. The experimental magnification is what? Well, actually, I measured the height of the image, and I got 1.3, right? So 1.3 centimeters. Then I divide that by the height of the object, 2.8. Right? So I'm actually measuring their heights, and I'm dividing them, I'm getting a ratio. Whereas in the theoretical, it's saying, okay, just take the predicted di theoretical, and then divide it by the dO. Then you're saying that it's predicted to be 34%. But now I'm actually, by drawing the lines, I'm actually getting an image, right? And then I'm dividing the height of that image by the object. So let's see what we get there. In my case, the image was 46% of the height of the image, 46% of the height of the object. So that means my image should have been a little bit closer to the lens. Both of my results would have been good. So one of the placements of my pins were probably wrong. If it was a little bit closer like this, if my di was a little bit smaller, then my image would also have been smaller, and then both results would have been good. So then you could do this again, and then look at your placement of the pins, right? So then, in that case, the percent error will be what? You can see that it illustrates the point. It teaches you the positive focal length, the negative focal length. It shows you how to calculate the focal length of the lens. And also it shows you how to theoretically, just by using pins and your eyesight, by just closing one eye, getting these lines to line up, these pins to line up, and hiding the image pin, finding out where the image is, and you can calculate a lot of things and prove a lot of things in optics theory, okay? Thank you very much.